Okay, we have charge Q1 at the given point, Q2 at the given point. We calculate the Coulomb's law of force. Okay, so, well, we calculate it. It's very straightforward. We plug 2 microcoulombs in for Q1, that goes here. We plug 6 microcoulombs in for Q2, that goes here. The vector here, we have 11 meters this way, 8 meters this way. That gives you 11 squared and 8 squared is 121 and 64, which is 185, unless I'm completely wrong about my calculation. So we have 185 meters squared for the magnitude of R12 squared. R12 is just the square root of 185 meters squared. We have our 11 meters times I, 8 meters times J, which is the R vector. And we put all that together, and we get something like 0.0006 newtons times 0.8I plus 0.6J. This is very approximate. That equals what? Well, I went up here. It's the 0.005 newtons times I plus 0.004 newtons times J. And let's just put a little arrow here. If we can get up here. Okay. Screw around that J there. Okay. Now, question. What if Q2 is 3 microcoulombs? Ignore the minus sign there for a minute. How would you calculate the force? Well, it's fairly obvious that the force is 6 microcoulombs here. So this is calculated based on 6 microcoulombs. If we calculate it based on 3 microcoulombs, well, Q2 is just a factor of the whole calculation. If Q2 becomes half as great, the whole calculation will come out half as great. So we can take half of the force, and we're going to get 0.0025 newtons, and this would be plus 0.002 newtons. Then if Q2 was negative 3 microcoulombs, what would it be? Well, then it would be negative of what we just said. Now, next question, what's F over Q2? Why would we want to know F over Q2? We're varying Q2. We're using different charges for Q2, figuring out what the force would be resulting from the charge Q1 here. If we're going to put different charges in here, let's go ahead and calculate F over Q2, and then we can just multiply that by whatever charge we want to put here to get the force, and we'll see how that works out.